Hello, and welcome to Game Theory. I'm Professor Naomi Utgoff of the United States Naval Academy. In this video, we'll define Nash equilibrium and use that definition to find Nash equilibria in Prisoner's Dilemma and Battle of the Sexes. On the first day of class, we played two games, the Dictator game and Prisoner's Dilemma. We discussed rather casually the motivations behind our play. In this video, we want to use the characteristics of economic agents, that they are selfish, rational, and intelligent, to determine what play we expect to see in a game. Here's Prisoner's Dilemma, again. When we played in class, we saw some mix of silence and confession. You correctly predicted that I, wearing my economic agent hat, would confess, since whatever my opponent does, my prison sentence is 1 year shorter when I confess. Using this kind of reasoning, we might anticipate that when both players are economic agents, both confess. Neither player will experience after-the-fact regret for confessing in the sense of wishing that she had been silent. Here's a new-to-us game, Battle of the Sexes. It's one of the many pieces of evidence that game theory is a discipline with its origins in a less egalitarian time. The man and the woman want to go on a date, either at a boxing match or the ballet. The man prefers boxing to ballet, and the woman prefers ballet to boxing, but most of all, they prefer being together. After work, this not being just a less egalitarian time, but also a time with no cell phones, each simultaneously and independently decides to go to the boxing match or the ballet. If they each go to the same place, the player at his or her non-preferred activity gets 1, while the player at her or his preferred activity gets 2. If they go to different places, they each get 0 because they are sad that they are not together. Economic agents prefer to somehow end up together, although it's difficult to say whether that means at the boxing match or at the ballet. Since they can't communicate before playing the game, there's a very real possibility that they will end up at different places. However, if they do somehow end up at the same place, neither player will experience after-the-fact regret in the sense of wishing that he or she had gone to the other place. Nash equilibrium is the formal term for play in which no player experiences after-the-fact regret. There are two logically equivalent ways we write down the definition of Nash equilibrium. The first says that a Nash equilibrium is a strategy profile such that, holding constant the strategies of all players but one, that one remaining player's strategy maximizes that player's payoff. The second way we express this idea is to say that the strategies in the strategy profile form mutual best responses. A player is best responding to others when she selects a strategy that she won't want to change after learning the other player's respective strategies. When all players best respond to each other, they are mutually best responding. Here's Prisoner's Dilemma. Using the definition of Nash equilibrium, let's check some different strategy profiles to see whether they are Nash equilibria. If both players confess, each receives -4. Confess is a Nash equilibrium. Importantly, -4 is not a Nash equilibrium. A Nash equilibrium is a strategy profile in which the strategies form mutual best responses. Therefore, when looking for Nash equilibria, we should specify strategy profiles, not the corresponding payoffs. Confess is a best response for player 1 when player 2 confesses. Player 1's only other option, silent, results in -5 for player 1, which is worse than -4. Player 1 doesn't regret her choice of confess. Another way to think about the lack of regret is that if we offered player 1, and only player 1, a do-over, she wouldn't switch from confess to silent. Similarly, confess is a best response for player 2 when player 1 confesses. Player 2's only other option, silent, results in -5 for player 2, which is worse than -4. Player 2 also doesn't regret her choice of confess. And also, if we offered player 2 and player 2 only a do-over, player 2 wouldn't switch from confess to silent. If both players are silent, each receives -2. Silent is not a Nash equilibrium. Silent is not a best response for player 1 when player 2 is silent. Player 1 has a profitable deviation to confess, since -1 is greater than -2. Player 1 regrets her choice of silent. If we offered player 1, and only player 1 a do-over, she would switch from silent to confess. Player 2 also has a profitable deviation to confess. If player 1 is silent and player 2 confesses, player 1 receives -5 and player 2 receives -1. Silent confess is not a Nash equilibrium. Silent is not a best response for player 1 when player 2 confesses. Player 1 has a profitable deviation from silent to confess, since -4 is greater than -5. Player 2 does not have a profitable deviation, but silent confess is still not a Nash equilibrium. A strategy profile is not a Nash equilibrium if even one player has a profitable deviation. A similar argument shows the confess silent is also not a Nash equilibrium. We have now checked all the strategy pairs and learned that confess-confess is the only Nash equilibrium in Prisoner's Dilemma. Here's Battle of the Sexes. We'll check together that boxing-boxing satisfies the definition of Nash equilibrium. If both players play boxing, the man receives 2 and the woman receives 1. Boxing-boxing is a Nash equilibrium. Boxing is a best response for the woman when the man goes boxing. The woman's only other option, ballet, results in 0 for her, which is worse than 1. The woman does not regret her choice to go boxing now that she knows, because they are together at the boxing match, that the man went boxing. If we offered only the woman a do-over, she would not switch to ballet because then she wouldn't get to go on a date at the boxing match. Similarly, boxing is a best response for the man when the woman goes boxing. The man's only other option, ballet, results in 0 for him, which is worse than 2. You should check that ballet-ballet is a Nash equilibrium, while boxing-ballet and ballet-boxing are not. One of the things we can conclude from these exercises is that Prisoner's Dilemma and Battle of the Sexes are structurally distinct in the sense that they have a different number of Nash equilibria. The other thing we can conclude from these exercises is that checking each strategy pair using the definition of Nash equilibrium is a time-consuming task. If we are going to make a study of what gameplay we can expect from economic agents, we need to develop some faster methods of finding Nash equilibria, especially for larger or otherwise more intricate games. Thanks so much for watching this video about the definition of Nash equilibrium and how to use that definition. In the next video, we'll introduce iterated elimination of strictly dominated strategies, another method for finding Nash equilibrium.